At the center of our galaxy, something is hiding. Not behind a veil of dust, not behind distance. Something that bends time itself around it like cloth pulled through a needle, that swallows light so completely the universe behaves, in that one spot, as though there is no universe at all. We have a name for it. We have a photograph of it. And yet, in every meaningful sense, we have no idea what it is. Its name is Sagittarius A star. 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. It sits roughly 26,000 light-years from where you are right now, anchoring the slow, majestic rotation of every star, every planet, every grain of cosmic dust in the Milky Way. Your own body is being pulled, gently and ceaselessly, toward it. The Earth circles the Sun. The Sun circles Sagittarius A star. And Sagittarius A star circles nothing at all. It is the still point. The drain at the bottom of our galactic bathtub, the thing around which everything we have ever known revolves. But what is it, really? For decades, astronomers spoke of it with a strange mixture of confidence and dread. They told us it was a supermassive black hole, and that was true. They told us its mass, and that was accurate. They told us we could not see inside it, and they meant it. Beyond the event horizon, that invisible line in spacetime where escape becomes mathematically impossible, physics as we understand it simply stops being useful. Equations break. Time stretches into something unrecognizable. The very concept of inside loses its shape. Whatever exists past that boundary is, by the strict definitions of science, unknowable. And yet we keep asking, because something is there. Something is doing the swallowing. In May of 2022, after years of work involving observatories scattered across the globe, the Event Horizon Telescope collaboration released an image that changed the conversation forever. A blurred ring of orange-gold light, a perfect dark circle at its center, the shadow of Sagittarius A star. For the first time in human history, we had looked into the face of the monster at the heart of our galaxy, and the monster had looked back. But that image, miraculous as it was, only deepened the mystery. The ring of light is hot gas spiraling toward annihilation. The dark circle is not the black hole itself, it is its shadow, the silhouette of an object so dense that the photons themselves cannot climb back out. What lies beyond that shadow is the real question, the question this video is about. If you have ever stared up at the summer sky in the direction of the constellation Sagittarius, and felt something pull at the edge of your attention, that pull is not metaphor. The center of the Milky Way really is there, behind the dust, behind the stars, behind everything. And inside that center, hidden from every telescope humanity has ever built or imagined, something waits. Over the next 15 sections, we are going to walk together to the edge of the most extreme environment in our galactic neighborhood. We will trace the story from the very beginning, from the moment a German physicist named Karl Schwarzschild scribbled a solution to Einstein's equations on a piece of paper during the First World War, to the radio astronomers in the 1970s who first detected a strange, compact source of energy at the galactic core. We will follow the scientists who spent 30 years watching individual stars whip around an invisible mass at speeds approaching a fraction of the speed of light. We will descend through the layers of what we know, the accretion disk, the photon sphere, the event horizon, and then, finally, we will step past the edge of physics, past the edge of language, into the place where, according to our best theories, every star, every world, every atom that has ever fallen in is still, in some sense, falling. Because here is the strange truth about black holes. They do not just hide things, they preserve them. According to one school of thought, every photon, every particle, every shred of information that has ever crossed the event horizon of Sagittarius A star is still encoded somewhere on the surface of that horizon. Trillions of years of cosmic history, stars torn apart, gas clouds devoured, possibly entire planets, possibly in the unimaginable future of our galaxy, possibly even us. And yet, according to a different school of thought, all of that information is gone, erased, forever. The two ideas cannot both be true. Some of the greatest minds in physics, Stephen Hawking among them, spent the better part of their careers wrestling with this contradiction. The argument is not settled. It may never be settled. But the answer, whatever it turns out to be, lives inside Sagittarius A star. Before we go any further, take a moment. If this is the kind of cosmic story you find yourself returning to, the kind that makes the world outside your window feel small and strange and beautiful all at once, consider subscribing. A tap on the like button helps these long, slow, careful explorations reach people who, like you, were built to wonder about things larger than themselves. There is no rush. The journey we are about to take is long. The view is worth it. What we are going to find in the sections ahead is not a single answer. It is a series of questions, each more disorienting than the last. We will learn why the spinning of Sagittarius A star tells us something profound about the early universe. We will learn why the gas falling into it behaves in ways no laboratory on Earth could ever replicate. We will learn why some physicists now suspect that what we call a black hole may not be a black hole at all, but something stranger, a doorway, a knot in spacetime, a place where the rules we cherish quietly cease to apply. We will learn about the firewall, the fuzzball, the singularity that may not exist, the information paradox that refuses to die. And we will learn, in the end, that the question of what lies inside Sagittarius A star is really a question about ourselves, about what we can know, about what the universe is willing to show us, about the silence at the center of everything. So let us begin where the story begins, not at the black hole, but at the idea of a black hole. Long before anyone had a telescope powerful enough to see one, before anyone even had a word for what they were imagining, a small group of physicists and mathematicians realized that something like this had to exist. Their journey to that realization is one of the strangest chapters in scientific history, and it is where our story truly starts. The story of Sagittarius A star begins, oddly enough, on a battlefield. The year was 1915. The First World War was grinding through its second winter, and on the Russian front, a 42-year-old German artillery lieutenant was suffering from a rare and painful autoimmune disease that was slowly killing him. His name was Karl Schwarzschild. Before the war, he had been the director of the Astrophysical Observatory in Potsdam, one of the most respected scientific institutions in Europe. He had volunteered for military service out of a sense of duty, and now, between calculating artillery trajectories and tending to the blistering sores covering his skin, he found time to read a paper that had just been published in Berlin. The paper was Albert Einstein's general theory of relativity. Einstein had spent nearly a decade working out a new description of gravity, one that replaced Isaac Newton's invisible forces with something far stranger. Gravity, Einstein said, was not a force at all. It was the curvature of spacetime itself. Massive objects bent the fabric of reality around them, and what we experienced as falling was simply the natural motion of things following those curves. The mathematics was brutal. The equations were so complex that Einstein himself had only managed to solve them in a single, approximate case. He doubted whether an exact solution was even possible. Schwarzschild, lying in a military hospital, took the equations and solved them. He did it within weeks. Working alone, in the cold, with shells thundering in the distance, he found an exact mathematical description of the spacetime around a perfectly spherical, non-rotating mass. He wrote it up and sent it to Einstein in a letter dated December of 1915. Einstein replied with a mixture of astonishment and admiration. He had not believed such a solution existed, and now here it was, scribbled on hospital stationery by a dying man. But Schwarzschild's solution contained something neither he nor Einstein fully understood. Buried in the mathematics was a strange boundary. At a certain distance from the center of the mass, a distance that depended only on how much mass was compressed into that point, the equations did something peculiar. Time, as measured from outside, slowed to a complete stop. Space and time seemed to swap roles, and inside that boundary, the mathematics described a region from which nothing, not even light, could ever return. Schwarzschild died in May of 1916, just months after sending his solution to Einstein. He never knew that the boundary buried in his equations would, half a century later, be called the Schwarzschild radius. He never knew that the strange region inside it would be called a black hole. He never knew that, 26,000 light-years from the hospital where he had done his calculations, a real object existed that obeyed his mathematics with terrifying precision. For decades after Schwarzschild's death, the strange solution sat in textbooks as a mathematical curiosity. Most physicists, including Einstein himself, refused to believe that such objects could actually exist in nature. The numbers worked, yes. But the idea that a star could collapse so completely that it tore a hole in the fabric of spacetime seemed absurd. It felt like a paradox, a glitch, something that the universe, in its better judgment, would surely never allow. That confidence began to crumble in the 1930s. A young Indian physicist named Subrahmanyan Chandrasekhar, traveling by ship from Madras to Cambridge to begin his graduate studies, worked out a calculation on the deck of the steamship that would shake the foundations of stellar physics. Chandrasekhar showed that there was a limit to how much mass a dying star could carry before its own gravity overwhelmed every force that normally held it up. Above that limit, now known as the Chandrasekhar limit, nothing could stop the collapse. Not the pressure of electrons, not the pressure of neutrons, not anything in the known catalogue of physics. The implication was staggering. If a star of sufficient mass ran out of nuclear fuel, it would not simply fade away. It would fall inward upon itself, faster and faster, until it crossed its own Schwarzschild radius and vanished from the visible universe entirely. Chandrasekhar published his results, and the establishment, led by the towering British astronomer Arthur Eddington, mocked him publicly. The idea was too strange, Eddington insisted. There must be a law of nature, as yet undiscovered, that would prevent such an absurdity. The universe simply could not behave that way. The universe, it turned out, did not particularly care what Eddington thought. By the late 1960s, decades of accumulating evidence had forced a quiet revolution in astrophysics. Stellar collapse was real. Compact objects were being discovered all across the sky. And in 1967, the American physicist John Archibald Wheeler, during a lecture at a conference in New York, casually used a phrase that had been floating around academic circles for a few years. He called these objects black holes. The name stuck. It captured something essential about what these things were: places of absolute darkness, absolute silence, absolute one-way travel. But while theorists were finally accepting that black holes could form from individual dying stars, a different question began to emerge from a different corner of astronomy. Radio astronomers, scanning the sky with newly built antenna arrays, were detecting strange, compact sources of energy at the centers of distant galaxies. The first hints came in the 1960s with the discovery of quasars, objects so bright that they outshone entire galaxies, yet so small that their light flickered on timescales of mere hours. Whatever was powering them had to be tiny by cosmic standards. And yet, the energy they released was unimaginable. Trillions of times the output of our sun, pouring out of a region smaller than our solar system. The only thing that could plausibly produce such a thing, the theorists realized, was a black hole, but not a stellar black hole, something far, far larger. Millions, perhaps billions, of times the mass of the sun, a new kind of object entirely. They began to call them supermassive black holes, and they began to suspect, tentatively at first, that such an object might lie at the heart of every large galaxy in the universe, including perhaps our own. In 1974, two American radio astronomers named Bruce Balick and Robert Brown turned a new instrument, the Green Bank Interferometer in West Virginia, toward the constellation Sagittarius, in the direction of the galactic center. The Milky Way's heart had always been frustratingly difficult to study. Visible light from that region is almost completely blocked by dust clouds along the galactic plane, dust that has accumulated over billions of years of stellar life and death. But radio waves can pass through that dust. And when Balick and Brown looked, they found something. A compact, intensely bright source of radio energy, sitting at the exact dynamic center of the galaxy. They named it, somewhat unimaginatively, Sagittarius A star, the asterisk distinguishing it from the broader Sagittarius A radio complex that had been known since the 1950s. At the time, nobody knew what they had found. It might have been a dense cluster of stars. It might have been a strange remnant of some ancient supernova. It might have been a supermassive black hole. But in 1974, that was still a fringe hypothesis. What Balick and Brown had done was put a dot on the map. They had pointed, with mathematical precision, at the place where our galaxy turns. The question of what was at that dot would consume the next half-century of astronomy, and the answer, when it finally came, would be stranger than anyone in 1974 had dared to imagine. For most of the 20th century, astronomers believed they understood, in broad strokes, what lay at the center of the Milky Way. The picture they painted was elegant, plausible, and as we now know, almost entirely wrong. The conventional wisdom went something like this. Galaxies, including our own, formed from vast collapsing clouds of hydrogen and helium in the early universe. As those clouds contracted, the densest material accumulated at the center. Stars formed first in those crowded inner regions, packed together at densities that would seem unimaginable from our quiet suburb of the galaxy. Over billions of years, that central population grew into what astronomers call the galactic bulge, a roughly spherical swarm of older, redder stars, all orbiting in tangled trajectories around the geometric center of the Milky Way. The center itself, in this picture, was simply more of the same. More stars, more gas. A particularly crowded knot of material at the bottom of the galaxy's gravitational well. There might be some interesting dynamics down there, the textbooks suggested. Perhaps a few exotic stellar remnants. Perhaps an unusually dense cluster of neutron stars and stellar mass black holes. But fundamentally, the center of our galaxy was understood to be a busy neighborhood, not a strange one. A place where ordinary physics, applied to a slightly more extreme population of stars, would account for everything we could measure. This was a comforting picture. It fit with what astronomers could see in nearby galaxies that they could study more directly. It fit with the broader story of galaxy formation that emerged from cosmological simulations in the 1970s and 80s. And critically, it required no new physics. The center of the Milky Way, in this view, was just the Milky Way, concentrated. There were, however, problems. Persistent, nagging problems that the conventional picture could not quite explain. The first problem was the radio source. Balick and Brown's 1974 detection of Sagittarius A star had revealed something the textbook picture did not predict. The radio emission was too compact. As radio astronomy techniques improved through the late 1970s, observers could pin down the size of the source with increasing precision. Whatever was emitting those radio waves was confined to a region smaller than our solar system. No cluster of stars, no matter how dense, could produce such a tightly focused signal. Stars take up space. A cluster of them, even a packed one, would smear the emission across light years. The Sagittarius A star signal was not smeared. It was a point. The second problem was energetic. The radio emission was not particularly bright by galactic standards, but it was steady, and it was unusual. The spectrum of the light did not match what stars produce. It did not match what supernova remnants produce. It did not match anything in the standard catalogue of galactic objects. The signal looked, to the trained eye, like the kind of synchrotron radiation produced when charged particles are accelerated to relativistic speeds in strong magnetic fields. The kind of thing you see, in fact, near the centers of distant active galaxies. The kind of thing theorists had begun to associate in the late 1970s with supermassive black holes. The third problem was motion. Astronomers had known for decades that gas clouds in the inner regions of the galaxy were behaving strangely. They were moving too fast. The orbital velocities of hydrogen and ionized gas, measured through their Doppler shifts, implied that something massive was anchoring them. Newton's law of gravitation is unforgiving. If you can measure how fast something is orbiting, and you can measure how far it is from the center of its orbit, you can calculate the mass at that center. The numbers, even from the relatively crude observations of the 1970s, hinted at a central mass of millions of suns, crammed into a region small enough that nobody could quite explain it. But the conventional wisdom was stubborn, and the conventional wisdom had a defense. The gas measurements were unreliable, critics argued. Gas in the inner galaxy is messy. It is heated, shocked, blown around by stellar winds and supernovae. You cannot trust gas to give you a clean reading of the underlying gravity. You needed something cleaner. You needed stars. This was the dilemma that defined galactic center astronomy through the 1980s. Everyone knew that the cleanest test of what lay at the center of the Milky Way would be to track the motions of individual stars in the inner few light years. If those stars were orbiting an ordinary distribution of mass, a dense star cluster, say, their motions would reveal it. If they were orbiting something concentrated, something small, something dark, their motions would reveal that too. The orbits would betray the truth. But there was a problem. You could not see the stars. The dust that obscures the galactic center in visible light is not a thin haze. It is a wall. 26,000 light-years of accumulated material, dense enough to dim the light from the galactic core by a factor of more than 1 trillion. Even the largest optical telescopes of the 1980s could not pierce that veil. The stars near Sagittarius A star were not invisible because they were faint. They were invisible because the universe had drawn a curtain across them. The conventional wisdom took refuge behind that curtain. As long as nobody could actually image the stars at the galactic center and track their motions, the question of what lay there remained, technically, open. Most astronomers in the 1980s, when asked what was at the heart of the Milky Way, would have said something cautious. A dense star cluster, probably. Perhaps with a modest black hole at its center, of the kind that forms from a single dying star. Nothing exotic. Nothing requiring a rewriting of the textbooks. A small minority disagreed. Theorists like Donald Lindenbell and Martin Rees in Britain, working in the late 1960s and early 70s, had argued on theoretical grounds that supermassive black holes should be common at the centers of galaxies. Their reasoning was elegant. If quasars were powered by supermassive black holes, and the evidence was mounting that they were, then the universe must contain billions of such objects, since quasars had clearly been more common in the early universe and must have left remnants. Those remnants would still be there, sitting quietly at the centers of ordinary galaxies, no longer feeding voraciously enough to shine as quasars, but still present, still massive, still waiting. Lyndon Bell, in a now famous 1969 paper, made a prediction that struck most of his contemporaries as wildly speculative. He suggested that essentially every large galaxy in the universe contained a supermassive black hole at its center. The Milky Way, he wrote, was almost certainly no exception. There should be one in our own backyard. For more than 2 decades, that prediction sat in the literature with no way to test it. The instruments did not exist. The technology to peer through the galactic dust and resolve individual stars at the center did not exist. The conventional wisdom that the heart of the Milky Way was a crowded but ordinary stellar neighborhood held its ground for one simple reason. Nobody could prove it wrong. The proof would require a new kind of telescope, a new kind of detector, a new kind of patience. It would require astronomers willing to commit decades of their careers to a single question, watching the same patch of sky night after night, year after year, waiting for the stars to give up their secret. It would require a technique that, in 1985, did not yet exist. That technique was about to be invented, and when it was, the conventional wisdom would not just be challenged, it would be destroyed. The first crack in the conventional picture did not come from a single dramatic observation. It came from a slow, accumulating discomfort, a sense, building through the 1980s, that the numbers were not adding up, that the picture of a benign, ordinary galactic center was a picture being held together by assumption rather than evidence. And the people who felt that discomfort most acutely were a small group of astronomers who had begun, against considerable skepticism, to take infrared astronomy seriously. Infrared light, unlike visible light, can pierce dust. The longer wavelengths slip past the obscuring grains that block shorter wavelengths. The way fog parts more easily for radio waves than for headlights. By the mid-1980s, infrared detector technology, much of it developed for military applications and slowly making its way into civilian astronomy, had reached a point where serious observations of the galactic center were finally possible. The dust that had hidden the heart of the Milky Way for the entire history of human astronomy was, at last, becoming transparent. Not fully, not in every wavelength, but enough. The first surprises came quickly. When astronomers pointed their new infrared cameras at the central few light-years of the galaxy, they did not see a smooth, featureless mass of stars. They saw structure. They saw individual stars, distinct from one another, clearly resolved. And many of those stars were young, bright, massive, hot blue stars that had no business being in the kind of ancient, settled stellar population the textbooks predicted. This was the first crack. Not a single anomaly, but a category error. The galactic center was supposed to be old. The bulge of the Milky Way is dominated by stars that have been burning for 10 or 12 billion years, the cosmic equivalent of a retirement community. But the infrared images revealed, sitting practically on top of Sagittarius A star, a population of stars that could not be more than a few million years old. Stars that, by the laws of stellar evolution, must have formed recently, right there, in the most hostile environment in the galaxy. The puzzle was profound. The region around Sagittarius A star is awash in tidal forces so violent that any gas cloud trying to collapse into a new star should be torn apart before gravity could overcome the disruption. Star formation, according to every model anyone had built, should be impossible there. And yet, the stars existed. They were visible. They were measurable. The galactic center was doing something the theorists had said it could not do. But the young stars were only the prelude. The real crack, the one that would split the old picture wide open, came when astronomers stopped just photographing those stars and started tracking them. In 1991, a German astronomer named Reinhard Genzel, working at the Max Planck Institute for Extraterrestrial Physics, began a campaign that would consume the next 30 years of his life. The idea was simple in concept and brutal in execution. He would point a telescope at the galactic center. He would photograph the same stars, the same patch of sky over and over again, year after year, and he would watch what they did. If those stars were orbiting an ordinary distribution of mass, their motions would be slow, gentle, indistinguishable from one observation to the next. If they were orbiting something compact and massive, they would move, visibly, measurably. They would betray, by the shape of their paths, exactly what was at the focus of their orbits. A few years later, on the other side of the Atlantic, an American astronomer named Andrea Ghez began an essentially identical project at the Keck Observatory in Hawaii, working with what was then the largest optical infrared telescope on Earth. Genzel and Ghez, working independently and to some extent competitively, set out to do something that had never been done before in the history of astronomy. They set out to watch stars orbit a black hole. The technique they used was called speckle imaging, later upgraded to a far more powerful method called adaptive optics. The Earth's atmosphere, even on the clearest night, is constantly churning. Air at slightly different temperatures bends light by slightly different amounts, smearing astronomical images into shimmering blobs. Adaptive optics fights back. Hundreds of times per second, a flexible mirror behind the telescope's main optics deforms in tiny, calculated ways, cancelling out the atmospheric distortion. The result is an image almost as sharp as if the telescope were in space. For the first time, astronomers could resolve individual stars within a fraction of a light-year of the galactic center. They could measure their positions to a precision of milliarcseconds. They could, if they were patient enough, watch them move. The first results, published in the mid-1990s, were startling. The stars were not just moving, they were sprinting. Some of them were traveling at speeds of thousands of kilometers per second, a substantial fraction of 1% of the speed of light. At those velocities, in that confined region, the gravitational mass anchoring them had to be enormous. Calculations gave a figure that, even to the people doing the calculating, seemed almost unbelievable. Several million times the mass of the Sun, concentrated in a region no larger than a few light days across. No cluster of stars could do that. No collection of stellar remnants could do that. Whatever was at the center of the Milky Way was not just dense, it was impossibly dense. The kind of density that, in the language of general relativity, has only one explanation. But the early measurements were not yet definitive. The stars had been observed for only a few years. The orbits, projected on the sky, looked like short, curved arcs, fragments of paths whose full shapes could only be guessed at. To prove what was happening, Genzel and Ghez needed to watch one of those stars complete a full orbit. They needed to see it swing around the central mass, reach its closest approach, and come back. Only then would the orbit fully constrain the geometry. Only then would the answer be undeniable. For most of the stars near Sagittarius A star, that would take centuries. Their orbits are long. Their periods, measured in human lifetimes, are essentially eternal. But there was one star. A single, peculiar object designated S2. It was close. Closer than any star anyone had expected to find that close to a presumed black hole. And its orbit, the early data suggested, was short. Possibly only a few years. Possibly within the working lifetime of the people watching it. S2 became the obsession of two competing teams on opposite sides of the planet. Genzel's group in Germany, observing from the European Southern Observatory's very large telescope in Chile. Gez's group in California, observing from Keck in Hawaii. Both teams tracking the same star. Both teams calculating, recalculating, refining. Both teams waiting for that one moment when S2 would swing past its closest approach to the central mass, its perihelion passage, and reveal, in the curvature of its path, exactly what it was orbiting. The waiting was not patient. There were arguments. There were rival publications. There were moments of public disagreement about whose measurements were more reliable, whose techniques were superior, whose interpretation was correct. But beneath the competition, something extraordinary was happening. The conventional picture of the galactic center, the picture that had held the textbooks together for half a century, was disintegrating in slow motion. Year by year, the data points piled up. Year by year, the arc of S2's orbit grew more complete. And year by year, the only explanation that fit the numbers became more singular, more inescapable, more strange. What lay at the center of our galaxy was not a star cluster. It was not a dense knot of remnants. It was not anything the conventional wisdom had been prepared to accept. It was, instead, the object that Schwarzschild had described in his hospital bed in 1915. The object that Lyndon Bell had predicted in 1969. The object that by the late 1990s was beginning to look less like a theoretical curiosity and more like the central, dominating fact of our galaxy. A supermassive black hole, right there, 26,000 light-years from your bedroom window, pulling on you gently even as you read this. To understand what came next, you have to understand the instruments. Because the story of Sagittarius A star is, more than almost any other story in modern astronomy, a story about technology. The black hole at the center of the Milky Way did not give up its secrets willingly. It gave them up only when humanity built machines extraordinary enough to force the question. The first such machine, in a sense, was the human eye attached to a large telescope. But the eye, even when extended by photographic plates and modern detectors, was never going to be enough. The galactic center, hidden behind its wall of dust, demanded something more. It demanded wavelengths the eye cannot see. It demanded resolution finer than any single telescope on Earth could deliver. It demanded a willingness to combine the light from instruments scattered across continents, treating the entire planet as a single observatory. And in the end, it demanded that astronomers build, in effect, a telescope the size of the Earth itself. The journey to that telescope began with adaptive optics, the technology that had made the orbit tracking work of Genzel and Gez possible. The principle behind adaptive optics is breathtaking when you stop to consider what it actually does. A bright star, or sometimes an artificially generated laser guide star, a column of sodium fluorescence excited high in the upper atmosphere, serves as a reference point. Sensors measure, hundreds of times per second, exactly how the light from that reference is being distorted by the air. A deformable mirror, its surface controlled by thousands of tiny actuators, reshapes itself in real time to counteract those distortions. The atmosphere is, in effect, subtracted from the observation. What remains is a view of the sky almost as clean as if you were floating above it. This was the technique that let the Keck telescope, perched on the summit of Mauna Kea in Hawaii, and the Very Large Telescope, on a mountaintop in Chile, resolve individual stars within a fraction of a light-year of Sagittarius A star. But adaptive optics alone, even on the largest telescopes, had a limit. The angular resolution of any single telescope is set by the diameter of its primary mirror and the wavelength of the light it observes. To see something as small as the actual shadow of Sagittarius A star, a disk about 50 microarcseconds across, as seen from Earth, you would need a telescope thousands of kilometers wide. No such telescope can be built. The Earth is not flat enough, the engineering is not feasible, and the cost would be unimaginable. Unless, of course, you cheat. The cheat is called Very Long Baseline Interferometry, or VLBI. The idea, first developed in radio astronomy in the 1960s and refined steadily over the following decades, is to take widely separated telescopes that, individually, are far too small to resolve fine detail, and link them together. Each telescope records the precise wavefront of the radio waves arriving from a distant source, along with an exquisitely accurate time stamp from an atomic clock. The recordings are later combined in a process called correlation, where powerful computers measure the tiny differences in arrival time between telescopes. Those differences, properly analyzed, reveal structure on angular scales determined not by the size of any single dish, but by the distance between the dishes, by the baseline. The longer the baseline, the finer the detail. In the early 2000s, a small group of radio astronomers, led by Shepard Doleman at the Massachusetts Institute of Technology, and later the Harvard-Smithsonian Center for Astrophysics, began to ask a question that bordered on audacious. What if you used the entire diameter of the Earth as a baseline? What if you linked radio telescopes in Hawaii, California, Arizona, Mexico, Chile, Spain, and the South Pole into a single, planet-spanning instrument? What if you observed at a millimeter wavelength, where the synchrotron emission from gas swirling around Sagittarius A star was bright enough to be detected, but short enough to resolve the black hole's actual shadow? The result would be a virtual telescope nearly 13,000 kilometers across, big enough in principle to see the event horizon. The project that grew out of this question was called the Event Horizon Telescope. It took more than a decade to assemble. Each participating observatory had to be upgraded with the most precise atomic clocks ever deployed at a radio site, hydrogen masers stable to within 1 second every 100 million years. Each had to record data at staggering rates, generating hundreds of terabytes per night, more than could be transmitted over the internet. The hard drives, after each observing run, were shipped physically by airplane to central processing facilities in Massachusetts and Germany, where the correlation was performed. The data from the South Pole, where flights are seasonal, sometimes had to wait 6 months before it could be retrieved. The observations themselves required almost supernatural cooperation from the weather. To work as a single instrument, all the participating telescopes had to have clear, dry skies simultaneously across 6 countries on 3 continents. The window of opportunity each year, when conditions might align, was a handful of nights in April. In April of 2017, that window opened. For 5 nights, the entire Event Horizon Telescope, spanning the planet, stared at the heart of the Milky Way and the heart of a distant galaxy called M87. The data from M87 came back first. In April of 2019, the world saw it, a blurred ring of orange light around a dark central shadow, the first image of a black hole. It made every newspaper on Earth. It became an icon, almost overnight, of what humans could do when they pointed enough telescopes at the same patch of sky and waited. But the image of Sagittarius A star, the one closer to home, took 3 more years to produce. The reason is revealing, and it tells you something about why our own galactic black hole is, in some ways, harder to study than far more distant ones. The black hole in M87 is a giant, 6.5 billion times the mass of the Sun. Gas falling into it does so slowly, in cosmic terms, taking days or weeks to circle around. The image stays stable. The Event Horizon Telescope could effectively take a long exposure and capture a steady picture. Sagittarius A star, by contrast, is small, only about 4 million solar masses. Gas at its event horizon completes an orbit in minutes. That means the structure of the bright ring around it changes faster than the telescope can collect enough light to image it. Trying to photograph Sagittarius A star is like trying to photograph a spinning fan with a long exposure. You do not get a clean image of a fan, you get a smear. The Event Horizon Telescope team spent 3 years developing new algorithms, techniques borrowed in part from medical imaging, in part from machine learning, to recover an image from data that was, by traditional standards, hopelessly variable. They simulated millions of possible configurations of gas around the black hole. They compared their simulations to the actual data. They averaged across the variability. And in May of 2022, they released the result. A second ring of orange-gold light, a second dark shadow, the face of our own galactic monster. The image, when you look at it, is uncannily similar to the one from M87. Same shape, same proportions, same dark void at the center, framed by the same hot ring of doomed gas. This was not a coincidence. It was a confirmation of one of the deepest predictions of general relativity. The shadow of a black hole, according to Einstein's equations, should look essentially the same regardless of size. A small black hole and a giant one should produce the same silhouette. And there it was. The math, written down in a hospital in 1915, was correct. But the instruments that confirmed it were not finished. They were, in fact, only beginning. Because seeing the shadow was one thing. Reading what was inside it was something else entirely. The first major discovery, the one that opened the floodgates for everything that followed, was the orbit of S2. It is the kind of discovery that, in retrospect, looks inevitable. Two teams, 16 years of patient observation, one star tracing a slow ellipse against the deep infrared background of the galactic center. But in the moment, it was anything but inevitable. It was the result of a long, contested, occasionally bitter scientific marathon. And when the result finally came, it did not just answer a question. It rewrote the textbook. By the late 1990s, both Genzel's team in Germany and Gez's team in California had accumulated enough observations of S2 to begin sketching the shape of its orbit. The star was clearly bound to something massive at the galactic center, and it was clearly moving fast. But the projected arc on the sky was still partial. The full geometry of the orbit, its true ellipse, its tilt with respect to our line of sight, the location of its closest approach to whatever it was circling, remained uncertain. The teams kept observing. The arc kept growing. In 2002, S2 reached perihelion, its closest approach to the central mass, the moment that the entire campaign had been built around. The numbers, when they came in, were extraordinary. At its closest, S2 had swept past Sagittarius A star at a distance of roughly 17 light-hours. That sounds like a lot, but in the geometry of the galactic center, it is astonishingly close. Closer than the distance from the Sun to the orbit of Pluto. At that moment, S2 was traveling at nearly 8,000 kilometers per second, more than 2.5% of the speed of light. A single, ordinary-looking star blazing past, an invisible something at speeds that no object in the solar system has ever approached. When the teams plugged those numbers into Kepler's laws and Newton's law of gravitation, the mass at the focus of the orbit came out to roughly 4 million times the mass of the Sun. And critically, that mass had to be contained within a region smaller than 17 light-hours across, because S2 had gone that close and emerged, intact, on the other side. Nothing diffuse could account for it. No cluster of stars, no swarm of stellar remnants, no exotic distributed mass could be packed that tightly without collapsing into a black hole on timescales far shorter than the age of the galaxy. The conclusion was no longer cautious. The conclusion was no longer hedged. There was a supermassive black hole at the center of the Milky Way, and S2 had just traced its gravitational signature in the most direct way physically possible. The scientific reaction was immediate, and it was loud. Papers appeared within months. Conference talks were rescheduled to accommodate the new results. The two teams, having spent more than a decade quietly competing, published nearly simultaneously, and for once the competition did not matter. The discovery was big enough to share. The black hole was real. The argument was over. But the reaction was not just about settling an old debate. It was about what came next. Because S2's perihelion passage was not merely a confirmation of the black hole's existence. It was a doorway into an entirely new kind of experimental physics. For the first time in history, astronomers had a clean, isolated test particle, a single star, on a well-determined orbit, swinging close enough to a black hole that the predictions of general relativity could be tested directly. Not in a laboratory, not in a simulation. In nature, at the heart of our galaxy, on a scale no human experiment could ever approach. The first test, completed over the following decade and a half, concerned a prediction Einstein had made in his original 1915 paper. General relativity says that light leaving a region of strong gravity should be redshifted, its wavelengths stretched, as it climbs out of the gravitational well. The effect is tiny in everyday circumstances. It is what GPS satellites have to correct for, fractions of a billionth of a second per day. But near a supermassive black hole, the effect should be substantial. When S2 swept through its perihelion in 2018, the second pass since regular monitoring began, both teams were ready. They were ready to measure not just the star's position, but its spectrum. They were ready to watch the redshift happen. It happened. The light from S2, as it whipped through its closest approach to Sagittarius A star, was shifted toward longer wavelengths by exactly the amount that general relativity predicted. Not Newton's amount, not classical physics' amount, Einstein's amount. The first direct measurement of gravitational redshift in the field of a supermassive black hole performed using a single star as a probe. The agreement with theory was, depending on which paper you read, between 99 and 100%. Einstein had been right again in a regime he had never lived to see tested. But that was not all. A second prediction of general relativity concerns how orbits behave near a massive body. In Newtonian gravity, an elliptical orbit closes on itself, the same path, traced again and again forever. In general relativity, near a strong gravitational source, the orbit does not quite close. Each ellipse rotates slightly relative to the previous one, an effect called precession. The phenomenon had been known since the 19th century, when astronomers noticed that the orbit of Mercury around the Sun precesses by a tiny amount each year. Einstein's general relativity, in 1915, had explained that precession exactly, and the explanation had been one of the first major triumphs of his theory. S2 should precess too, far more dramatically than Mercury, because the gravitational field it experiences is far stronger. The prediction was that, after each close passage past Sagittarius A star, the orientation of S2's ellipse should shift by a measurable amount. In 2020, after analyzing nearly 3 decades of data from the Very Large Telescope, Genzel's team announced that they had detected the precession. The orbit of S2 was, in fact, rotating exactly as general relativity demanded. Another prediction confirmed. Another test passed. The implications cascaded outward. If general relativity worked this well around a 4 million solar mass black hole, then the framework astronomers were using to interpret everything else they were seeing, the dynamics of gas, the structure of the accretion flow, the geometry of the shadow eventually imaged by the Event Horizon Telescope, was solid. The mathematics could be trusted. The strange, counterintuitive predictions of curved spacetime were not academic abstractions. They were happening, demonstrably, 26,000 light-years from Earth, and the work was not done. By the time S2 completed its third observed perihelion passage, the teams had begun to push for even more sensitive tests. They began to ask whether the shape of the orbits could reveal the spin of the black hole, not just its mass. They began to ask whether the entire stellar swarm near Sagittarius A star, the so-called S-stars, might collectively carry information about the gravitational field that no single orbit could provide. They began to push the technology to integrate multiple instruments, including a new interferometric mode at the Very Large Telescope called gravity, which combined the light from 4 giant telescopes into a single effective aperture, into a sensitivity regime that no previous generation of astronomy had even contemplated. Andrea Ghez and Reinhard Genzel in 2020 were awarded the Nobel Prize in Physics for their work, sharing it with Roger Penrose, whose theoretical work decades earlier had laid the mathematical foundation for the existence of black holes. The citation was specific. The prize was awarded for the discovery of a supermassive compact object at the center of our galaxy, not a black hole, technically. The Nobel Committee, scrupulous about word choices, used the more cautious phrase, but everyone in the room knew what they meant. Everyone in the field knew what S2 had shown. The thing at the center of the Milky Way was real. It was the size that Schwarzschild's math demanded. It was the kind of object that, according to every known law of physics, had only one possible interpretation: a black hole, 4 million solar masses, 26,000 light-years away. And quietly, almost gently, pulling the entire galaxy into a slow, gravitational waltz around itself. But this, as it turned out, was only the beginning of what we would learn. The second discovery was stranger, and it concerned not the orbit of a star, but the behavior of light. Specifically, the strange, flickering, unpredictable behavior of the radiation coming from Sagittarius A star itself. For decades, astronomers had assumed that the radio source first detected by Balick and Brown in 1974 was relatively quiet. A supermassive black hole sitting at the center of an old, well-settled galaxy was not supposed to be doing much. Unlike the violent, active galactic nuclei of quasars, which devour gas at prodigious rates and blaze across the universe, Sagittarius A star appeared to be in a state of cosmic dormancy. It was feeding, yes, but feebly. The bulk of the radio emission came from a thin, ragged stream of hot gas captured from the winds of nearby stars, falling inward at a trickle. By the standards of black holes elsewhere in the universe, Sagittarius A star was a sleeper, a pensioner, a faded giant. That picture began to crack in 2000. A team of astronomers, observing Sagittarius A star with the Chandra X-ray Observatory, a space telescope launched the previous year to study the high-energy universe, caught something unexpected. The black hole, normally dim in X-rays, suddenly flared. For about 3 hours, the X-ray emission from Sagittarius A star brightened by a factor of nearly 50. Then it faded back to its quiet baseline, as if nothing had happened. This was not supposed to happen. A black hole feeding at a steady, low rate should produce a steady, low signal, not bursts, not flares, not the kind of dramatic, transient behavior that suggested something violent was occurring just outside the event horizon. The astronomers who caught the flare did not quite know what to make of it. Was it a stray X-ray burst from an unrelated source nearby, contaminating their measurement? Was it some kind of instrumental glitch? Or was it real? It was real. Over the next several years, as more observations accumulated, the pattern became unmistakable. Sagittarius A star flares. It flares often. The X-ray brightness can jump by factors of 10, 50, occasionally even 100, for periods ranging from minutes to hours, and then subside. Infrared flares follow a similar pattern. So do flares at millimeter wavelengths. The flares occur on average once a day, sometimes more, sometimes less. And the cause, despite years of investigation, remains only partially understood. What is clear is that the flares are produced very close to the event horizon. The timescales of the brightening and fading correspond, in general relativity, to the time it takes light to cross a region only a few times larger than the black hole itself. Whatever is happening, it is happening in the innermost, stable orbit, the doomed last loop of gas before it disappears past the boundary. The flares are the death cries of matter in the moment before it falls in. The mechanism that produces them is thought to involve magnetic reconnection, the same physical process that drives solar flares on the surface of the sun, but operating in a gravitational regime so extreme that the gas itself is shredded by tidal forces as the magnetic field rearranges. Loops of magnetic field, twisted and stretched by the differential rotation of the accretion flow, snap and reconnect. The energy released accelerates electrons to nearly the speed of light, and those electrons radiate furiously across the entire electromagnetic spectrum on their way into oblivion. But the flares were only the first hint of the second discovery. The deeper, more unexpected layer came when astronomers began to monitor Sagittarius A star with the gravity instrument, the same interferometric system at the very large telescope that had refined the orbital measurements of S2. Gravity can track the position of a flare on the sky with a precision of about 10 microarcseconds. That is staggeringly fine. At the distance of the galactic center, it corresponds to a spatial scale of just a few times the size of the black hole's event horizon. In 2018, gravity caught 3 flares in rapid succession, and it did not just measure their brightness. It measured where, on the sky, the the centroid of the emission was located, moment by moment, as the flares unfolded. The result was uncanny. The flares were moving, not just brightening and fading, but actually traveling in a small, looping pattern on the sky, completing a circular motion in roughly 45 minutes. The interpretation, announced by the gravity team, was that the team was watching individual hot spots of gas orbit Sagittarius A star at a distance of only 6 to 10 times the black hole's gravitational radius. The orbital speed implied by the motion was roughly 30% of the speed of light. And critically, the direction of the motion, counterclockwise on the sky, with a specific tilt, matched almost exactly the orientation that other observations had predicted for the inner edge of the accretion flow. This was the deeper discovery. Not that the black hole flares, but that astronomers had, for the first time, directly imaged matter circulating around an event horizon. The motion of those flares was, in effect, a stopwatch held up against the geometry of curved spacetime itself. The orbital period gave a direct measurement of the rotational structure of the inner accretion flow. The shape of the path, when carefully analyzed, hinted at the spin of the black hole. The very fact that the gas could maintain stable orbits at such close range told astronomers something profound about the way matter behaves at the edge of the abyss. And there was more. The motion of the flares, observed in detail, did not behave like ordinary orbital motion. The light from the hot spots was being bent, distorted, and amplified by the extreme gravitational lensing of the black hole itself. As a flare came around the side of the black hole closest to us, its light was beamed in our direction by relativistic effects, making it appear brighter. As it swung around to the far side, its light was bent over the top of the black hole and reached us anyway, ghostly and shifted. The team could see, in the data, the fingerprints of general relativity not as an abstraction, but as a measurable distortion of how light moves through curved space. The implications were profound. For decades, the inner regions of black holes had been theoretical playgrounds, places where calculations were done, simulations were run, and predictions were made, but where no direct observation could ever be brought to bear. With the gravity observations of the flares, that changed. The inner accretion flow of Sagittarius A star was no longer an abstraction. It was a physical environment that could be probed, mapped, and measured. Gas was orbiting at relativistic speeds, light was being warped by gravity in real time, and humans on Earth were watching it happen. But the flares also raised an uncomfortable question. If Sagittarius A star is producing these dramatic events on a daily basis now, in its quiet, dormant state, what was it doing in the past? When the galactic center was younger, when more gas was available to feed it, when nearby gas clouds occasionally tumbled in from larger distances, what was the black hole like then? The first answers to that question began to emerge in the 2000 teens, and they were unsettling. Astronomers studying gamma-ray emission from above and below the galactic plane discovered enormous structures, each tens of thousands of light-years tall, extending outward from the galactic center. The structures were dubbed the Fermi bubbles, after the Fermi gamma-ray space telescope that found them, and their interpretation was clear. They were the fading remnants of an enormous outflow, a jet, or a wind, or both, that had erupted from Sagittarius A star several million years ago, when the black hole was feeding far more vigorously than it is today. In the more distant past, perhaps tens of millions of years ago, the central black hole of our galaxy was not the sleepy giant we observe now. It was active, it was loud, it was, in some sense, alive. The pattern was starting to emerge. Sagittarius A star was not a static object, but a dynamic one. It changes, it fluctuates. It has a history written in light and gas, and that history was just beginning to be read. The third discovery did not arrive as a single moment of revelation. It emerged slowly, over the course of nearly 2 decades, from a patient comparison of one black hole to many others. And what it revealed was that the strange creature at the center of our galaxy was not strange at all. It was, in fact, a member of a vast cosmic family, and the more astronomers studied that family, the more they realized that the entire structure of the universe was tangled up with the lives of supermassive black holes. The first hint came in the late 1990s, when astronomers using the Hubble Space Telescope began to systematically survey the centers of nearby galaxies. They were looking for the same telltale signature that S2 had revealed in our own galaxy: rapidly orbiting stars, gas swirling at impossible speeds, the gravitational fingerprint of a compact mass concentrated at the geometric center. They found it almost everywhere they looked. Galaxy after galaxy, from giant ellipticals to ordinary spirals like the Milky Way, harbored a supermassive black hole at its heart. Lyndon Bell's audacious 1969 prediction had been correct. The black holes were ubiquitous, but that, in itself, was not the discovery. The discovery came when astronomers began to compare the masses of those black holes to properties of the galaxies that hosted them, and they found, to their astonishment, a relationship. A clean, tight mathematical correlation that no one had predicted and no one could initially explain. The correlation went like this. The more massive a galaxy's central bulge, the dense, roughly spherical concentration of old stars at its core, the more massive its central black hole. Not approximately, not loosely, precisely. The ratio held across more than 4 orders of magnitude in black hole mass, from small galaxies harboring black holes of a few 100,000 solar masses to giant ellipticals with central black holes weighing billions of suns. A second, even tighter version of the correlation linked the black hole's mass to the random motions of stars in the galactic bulge, measured by the spread of their velocities, what astronomers call the velocity dispersion. The relationship, known as the M-sigma relation, was published in 2000 by 2 teams working independently, one led by Karl Schwarzschild at the University of Texas and the other by Laura Farias and David Merritt. Why this should be true was not obvious. The central black hole, even one as massive as Sagittarius A star, contains less than 1% of the mass of the galaxy as a whole. Its gravitational influence is dominant only in the innermost few light years, a region utterly dwarfed by the galaxy itself, which stretches across 100,000 light years. How could a tiny, hidden object at the center of a vast stellar system know anything about the bulk properties of that system? How could the galaxy and the black hole conspire to grow in such precise proportion? The answer, as it emerged through years of theoretical modeling and observational follow-up, was that the black hole was not a passive bystander in the life of its galaxy. It was an active participant. When supermassive black holes feed at high rates, when they become quasars, devouring gas and shining across the universe, they release prodigious amounts of energy. Some of that energy heats the surrounding gas. Some of it drives outflows, winds and jets that blast through the host galaxy and out into intergalactic space. And those outflows, the modeling suggested, were powerful enough to expel gas from the galactic bulge, choking off star formation and limiting the future growth of both the galaxy and the black hole itself. It was a feedback loop. The black hole grew by accreting gas. The accretion drove energy back into the galaxy. The energy heated and expelled gas, slowing both the growth of the black hole and the formation of new stars. The two evolved together, locked in a slow, billion-year dance, until they arrived at the proportions the M-sigma relation describes today. The implications for the Milky Way were stark. The Sagittarius A star at the center of our galaxy was not just a curiosity. It was, in some sense, a witness to the entire history of the Milky Way. Its mass, 4 million solar masses, was set in part by how vigorously it had fed in the past, and by how violently it had pushed back against its own galactic environment. The Fermi bubbles, those enormous gamma-ray structures discovered above and below the galactic plane, were the most recent evidence of that pushback. They were the latest belch of a creature that had been feeding, intermittently, for more than 10 billion years. But the third discovery was not just about how black holes and galaxies grow together. It was about how they were born together, and how their entire family tree might trace back to the earliest moments of cosmic history. In 2021, the James Webb Space Telescope began returning images of the most distant galaxies ever observed, galaxies whose light had been traveling for more than 13 billion years, beginning its journey when the universe was less than 5% of its current age. The astronomers operating the telescope expected to find young, small, simple galaxies in those early epochs, only just beginning to assemble. What they found, instead, was startling. Many of those early galaxies already harbored supermassive black holes. Some of those black holes were enormous, millions or even billions of solar masses, at a time when the universe was barely old enough for such monsters to have formed by any conventional process. The discovery upended the timeline. The standard picture had assumed that supermassive black holes grew slowly from smaller seeds over billions of years of steady accretion. But the James Webb observations showed black holes that were already gigantic when the universe was less than 1 billion years old. There simply had not been enough time for them to grow that way. Something else, some other mechanism, had to be involved. Perhaps the seeds themselves were already massive, collapsing directly from primordial gas clouds without ever passing through a stellar phase. Perhaps the early universe had been a more chaotic, gravitationally violent place than anyone had imagined. Whatever the answer, the existence of giant black holes in the early universe meant that Sagittarius A star was not just a member of a cosmic family. It was the descendant of an ancient lineage stretching back to nearly the dawn of time. And that lineage was about to reveal something even more profound. Beginning in 2023, a new kind of observation entered astronomy: the detection of low-frequency gravitational waves, the cosmic rumble produced by pairs of supermassive black holes spiraling toward merger across the universe. Pulsar timing arrays, networks of millisecond pulsars whose extraordinary rotational stability allowed astronomers to detect tiny distortions in spacetime passing through the galaxy, had spent more than 15 years gathering data. When the data was finally analyzed, it revealed a background hum of gravitational waves consistent with millions of supermassive black hole binaries scattered across the observable universe, all slowly inspiraling toward eventual collision. The picture this painted was breathtaking. Throughout cosmic history, galaxies have collided and merged. Each merger brings two supermassive black holes together at the new galaxy's center. Over millions of years, the black holes spiral inward, eventually merging into a single, larger black hole. The cycle repeats. The black hole at the center of every galaxy today, including Sagittarius A star, is almost certainly the result of multiple such mergers stretching across cosmic time. Our own galactic black hole, in other words, may not be a single object at all. It may be a composite, the gravitational sum of many smaller black holes that have spiraled together over billions of years. Each merger would have released a burst of gravitational waves that propagated across the universe, rippling through spacetime, carrying away energy and momentum. Some of those waves might still be detectable today, encoded in the timing of distant pulsars or the residual hum picked up by future gravitational wave observatories. The third discovery was the dawning realization that Sagittarius A star was not an isolated phenomenon. It was a node in a vast cosmic network. Every supermassive black hole in the universe was, in some sense, related, products of the same fundamental processes, shaped by the same feedback loops, linked by gravitational interactions stretching across billions of light years. And the strange, quiet object at the center of the Milky Way was simply our nearest example. A representative, in some sense, of an entire population, a window into how all galaxies and all black holes came to be. The pattern was unmistakable now, but it was also, in some ways, only making the central mystery more acute. Because if Sagittarius A star was typical, then whatever was inside it, whatever lay beyond that dark shadow imaged by the Event Horizon Telescope, was happening, right now, at the center of every galaxy in the observable universe. The fourth discovery is the one that haunts physicists. It is the one that, more than any other finding about Sagittarius A star or its cousins across the universe, refuses to fit cleanly into any framework we currently possess. It is not a discovery in the usual sense, not a single observation, not a single measurement. It is, rather, the slow accumulation of a paradox. A contradiction so deep that some of the greatest minds of the past half-century have devoted their entire careers to it, and the contradiction has not yielded. It has only sharpened. To understand it, you have to go back to 1974. to a young British physicist named Stephen Hawking, who, while trying to apply the rules of quantum mechanics to the immediate vicinity of a black hole's event horizon, made a calculation that horrified him. The calculation went like this. Quantum mechanics tells us that empty space is not really empty. The vacuum, at the smallest scales, is a roiling sea of so-called virtual particles, pairs of particles and antiparticles that flicker into existence briefly and then annihilate one another and vanish. They are not detectable directly. They are, in some sense, mathematical bookkeeping rather than physical objects, but their effects are measurable. They produce tiny corrections to atomic energy levels, observable forces between metal plates in a vacuum, subtle features of laboratory experiments. The virtual particles are real in the only sense that matters in physics. Hawking asked a simple question. What happens to those virtual particle pairs when they appear right at the edge of a black hole's event horizon? What happens when one of the two particles forms just outside and the other forms just inside? The answer, when he worked it out, was extraordinary. The particle inside the horizon would fall in and be lost forever. The particle outside, no longer able to annihilate with its partner, would be liberated. It would escape the black hole, carrying energy away with it. From the perspective of a distant observer, the black hole would appear to glow faintly, to radiate, to emit a thin stream of particles, slowly and steadily, as if it were a hot object cooling into a cold universe. This was the discovery of what came to be called Hawking radiation, and it had a consequence that nobody, including Hawking himself, immediately appreciated. If a black hole radiates, then it loses energy. If it loses energy, by Einstein's most famous equation, it loses mass. Over an unimaginable span of time, far longer than the current age of the universe, but finite, the black hole would evaporate completely. It would shrink faster and faster as it lost mass, until in a final burst it would disappear from existence. For Sagittarius A star, the timescale is staggering. A black hole of 4 million solar masses would take roughly 10 to the 87th power years to evaporate by Hawking radiation. That is a number so vast that no human metaphor adequately captures it. But the timescale is not the point. The point is the principle. The principle is that black holes are not eternal. They are processes, they have lifespans, and at the end of those lifespans they vanish, leaving behind only a faint cloud of escaping particles. It is what those escaping particles carry, or do not carry, that constitutes the paradox. In quantum mechanics, information is not supposed to be destroyed, ever. The principle is called unitarity, and it is one of the most fundamental rules of physics. If you know the precise quantum state of a system at any moment, you can in principle calculate, with perfect accuracy, what its state will be at any other moment. The information that defines the system is preserved. It can be scrambled, hidden, mixed up beyond any practical possibility of recovery, but it cannot be erased. The universe, at its deepest level, keeps a perfect record of everything. Black holes appear to break this rule. Consider what happens when a star falls into Sagittarius A star. The star carries an enormous amount of information, the arrangement of every atom, the quantum state of every electron, the patterns of every interaction that ever shaped that star, going back to its formation in some long-vanished molecular cloud billions of years ago. When the star crosses the event horizon and is consumed, that information is, at minimum, hidden from the outside universe. Whatever falls past the horizon is, by the standard definition, beyond retrieval. But then the black hole slowly evaporates by Hawking radiation. And here is the problem. The radiation, according to Hawking's original calculation, is thermal. It is featureless. It carries no information about what fell into the black hole. It is just a slow, structureless drizzle of particles, indistinguishable whether the black hole consumed a star, a planet, a library, or an entire civilization. When the black hole finally evaporates and disappears, all that is left behind is this featureless radiation. The information about everything that ever fell in is gone. Quantum mechanics says that cannot happen. Hawking's calculation says it does happen. The two cannot both be right. This is the black hole information paradox. It is, by some measures, the deepest unsolved problem in theoretical physics. It has resisted resolution for more than 50 years. It has driven the development of entire branches of mathematics, string theory, loop quantum gravity, and holographic theories of spacetime. It has provoked some of the most spectacular wagers and debates in modern science, including a famous bet between Hawking, Kip Thorne, and John Preskill that took 30 years to resolve. It has, at various moments, seemed almost solved, then unsolved, then solved again, then unsolved. And Sagittarius A star is, in some sense, the testing ground. Not because we can actually wait 10 to the 87th years for it to evaporate, but because the same physics applies on smaller scales in slightly different regimes, and because the existence of a real black hole in our cosmic neighborhood concentrates the mind on what is actually at stake. The paradox is not a thought experiment. It is something that, in some form, is happening right now at the center of our galaxy, every time a particle crosses the event horizon, and every time a photon of Hawking radiation escapes into the surrounding space. Several proposed resolutions have emerged. One school of thought, building on ideas developed in the late 1990s and refined steadily since, suggests that the information is not destroyed, but encoded, in extraordinarily subtle ways, in correlations between the outgoing Hawking radiation particles. The radiation, in this view, is not truly featureless. It only looks featureless to anyone unable to perform impossibly precise measurements on every photon emitted across the black hole's entire history. The information is there. It is just smeared out across the radiation in a way that, in practice, can never be recovered. Another school suggests that the inside of a black hole is not really inside in the way we usually mean. According to the holographic principle, first proposed in the early 1990s and developed dramatically by Juan Maldacena in 1997, the interior of a black hole is, in some sense, a projection of information encoded on its surface. The event horizon, in this view, is the real object. The interior is a kind of illusion, a useful description for things falling in, but not the fundamental reality. The information never really crosses the horizon. It is always there, painted on the surface, accessible in principle to anyone with the right tools to read it. A third school, more radical, suggests that the event horizon itself does not exist in the way classical general relativity describes. Instead of a smooth, featureless boundary that an infalling observer would cross without noticing anything, the horizon might be a wall of intense quantum activity, what physicists have called a firewall, that destroys any infalling matter and emits the information back into space. Whether or not anything called a singularity exists at the center is, in this picture, irrelevant. The black hole's secrets are not in its interior, they are at its surface. None of these proposals is fully accepted. None has been tested. They are all attempts to reconcile a contradiction that we have known about for half a century and have not yet been able to resolve. And the contradiction, sitting right there in the heart of the Milky Way, is real. Sagittarius A star, at this very moment, is consuming information and slowly bleeding away particles, and the universe is keeping some kind of record, somehow, in a way we have yet to understand. The mid-video climax, the discovery that, more than any other, reframes everything we thought we understood about the heart of our galaxy, concerns the spin. For decades, when astronomers spoke about Sagittarius A star, the discussion was overwhelmingly about its mass. Mass was the easy quantity. Mass was what the orbits of stars revealed. Mass was what the equations needed first. The number 4 million solar masses became iconic, repeated in textbooks, dropped into documentaries, recited at the beginning of every conference talk. It was the headline fact, the thing everyone knew about the black hole at the center of the Milky Way. But mass, it turns out, is only half the story. According to general relativity, a black hole is fully described by just three quantities: its mass, its electric charge, which, for any realistic astrophysical black hole, is essentially zero, because any net charge would be quickly neutralized by attracting opposite charges from the surrounding plasma, and its spin. The mathematical theorem expressing this is called the no-hair theorem, and it has a strange, almost poetic quality. A black hole, John Wheeler famously remarked, has no hair. Whatever complexity, whatever variety, whatever individual character may have characterized the matter that fell in is erased. What remains is a smooth, featureless object that can be summarized by two numbers: mass and spin. For Sagittarius A star, the spin remained, until very recently, almost completely unknown. The mass had been pinned down with extraordinary precision through the orbits of S2 and its sister stars, but the spin was harder. The spin does not announce itself in the motion of distant orbiting bodies. It expresses itself in subtler ways, in the geometry of light bent near the event horizon, in the orientation of the accretion flow, in the polarization of radiation produced by gas spiraling inward. To measure the spin, astronomers needed observations of a different kind, focused not on stars at light-hour distances, but on matter touching the very edge of the horizon itself. The Event Horizon Telescope, having captured its iconic image of Sagittarius A star in 2022, immediately set to work on this problem. The shadow of a spinning black hole, in theory, is not perfectly circular. It is slightly asymmetric, flattened on the side where the rotating spacetime drags light against its motion, brightened on the side where the rotation carries the emitting gas toward us. The asymmetry is subtle. Detecting it requires sensitivity at the very edge of what the Event Horizon Telescope can deliver. But the team had collected enough data over multiple observing campaigns to begin extracting an answer. In 2024, the team announced their initial results on the spin. Sagittarius A star, they reported, is rotating, not slowly, not modestly. The black hole at the center of our galaxy is spinning at a substantial fraction of the maximum rate allowed by general relativity itself. The data suggested a dimensionless spin parameter. Astrophysicists call it a star, somewhat confusingly, of roughly 0.9, where 1 would represent the theoretical maximum and 0 would represent no rotation at all. This was a stunning result. And it had implications that cascaded outward, touching every aspect of how astronomers understood the black hole and its history. To understand why, you have to understand what a maximally spinning black hole actually means. According to general relativity, a black hole's rotation drags spacetime itself around with it, in a phenomenon called frame dragging. The faster the rotation, the more extreme the dragging. At spins close to the theoretical maximum, the region of dragged spacetime extends well beyond the event horizon, into a zone called the ergosphere, a place where it is impossible to remain stationary relative to the distant universe, because spacetime is being pulled around the black hole faster than light itself can travel against the rotation. Inside the ergosphere, you can still escape outward if you have enough thrust, but you cannot resist being carried along with the spin. A rapidly spinning supermassive black hole, in other words, is not just sitting at the center of its galaxy. It is actively churning the very fabric of spacetime around it, in a region tens of times larger than the event horizon itself. Every photon, every gas particle, every magnetic field line in that region is being twisted, accelerated, and reshaped by the rotation. But there was something else. Something that the spin measurement seemed to imply about the orientation of Sagittarius A star. The axis of rotation, the team's analysis suggested, was tilted at a substantial angle to the plane of the Milky Way. The black hole was not spinning in the same direction the galaxy rotates. It was spinning at an angle, as if the entire central engine of our galaxy were canted, oriented along some axis that has nothing to do with the disk of stars surrounding it. This was deeply unexpected. If Sagittarius A star had grown primarily by feeding on gas from the surrounding galactic disk, you would expect its spin axis to align, more or less, with the rotation axis of the disk itself. The gas would have carried angular momentum into the black hole in a more or less coherent direction over billions of years, gradually aligning the spin with the galactic plane. The fact that the spin appears to be tilted suggests that this is not what happened. Or not entirely. The most likely explanation involves the history described in earlier sections. Sagittarius A star, like most supermassive black holes, probably grew through a combination of slow accretion from its surroundings and occasional mergers with other black holes. A merger between two black holes does not just add mass. It produces a new black hole whose spin can point in essentially any direction, depending on the orientations and orbital geometries of the original pair. If Sagittarius A star is the result of one or more mergers in the past several billion years, those events would have completely reset its spin axis, potentially leaving it tilted relative to the surrounding galaxy. In other words, the tilt of the spin is a kind of fossil. It is a record of the violent, ancient history of our galactic center. Encoded in the orientation of Sagittarius A star's rotation is the memory of past collisions, past mergers, past dramatic events that reshaped the heart of the Milky Way long before any human existed to wonder about it. The black hole, in the most literal sense, is wearing its history on its sleeve, or rather, on its axis. There were other implications, equally profound. A rapidly spinning supermassive black hole stores an enormous amount of rotational energy. Far more, in fact, than the equivalent in mass. By some estimates, more than 20% of the total mass energy of a maximally spinning black hole is locked up in its rotation. That energy is not stuck there forever. Through a process first identified theoretically by Roger Penrose in 1969, and later refined by Roy Kerr and others, rotational energy can be extracted from a spinning black hole. Matter falling into the ergosphere can, under the right conditions, carry away more energy than it brought in, harvesting the difference from the black hole's rotation. The black hole slows. The matter accelerates outward, sometimes to extraordinary speeds. This is, almost certainly, the mechanism that powers the relativistic jets observed in some active galactic nuclei. And it suggests that Sagittarius A star, when it was more actively feeding in the past, was capable of launching tremendous outflows powered by its own rotation. The Fermi bubbles, those enormous gamma-ray structures above and below the galactic plane, may be more than just the residue of past accretion. They may be the fading echo of a time when Sagittarius A star's spin was being actively tapped, hurling matter and energy across thousands of light years. And there is one more implication, more speculative, more contested, but worth mentioning. A rapidly spinning black hole has a more complex internal geometry than a non-rotating one. The interior, according to general relativity, contains not a single point-like singularity, but a ring-shaped one, surrounded by regions where the equations of physics behave in ways even more counterintuitive than the standard picture allows. Some physicists have suggested, on theoretical grounds, that the interior of a rapidly rotating black hole might contain so-called closed time-like curves, paths through spacetime that loop back on themselves, allowing, at least mathematically, a kind of time travel. Whether such structures actually exist inside Sagittarius A star, or whether quantum effects we do not yet understand prevent them from forming, is unknown. But the spin measurement makes the question more than academic. It places the question, concretely and specifically, at the center of our galaxy. The mid-video climax, then, is not just that Sagittarius A star is rotating. It is that the rotation reframes everything. The history of the black hole, written in its tilt. The energy stored in its spin, capable of powering galactic outflows. The interior geometry, made stranger and more paradoxical by the rotation than any non-spinning model could produce. The peaceful, dormant giant at the center of our galaxy is, beneath that quiet exterior, a churning engine of warped spacetime, storing enough rotational energy to potentially reshape entire regions of the Milky Way, oriented along an axis that remembers ancient collisions, harboring an interior whose true nature remains beyond our current theories. Sagittarius A star is not just a black hole. It is a witness. It is an engine. It is, in some sense, a portal into questions about the universe that we have only begun to learn how to ask. The discoveries of the past 3 decades have done more than reveal what lies at the center of our galaxy. They have systematically dismantled assumptions about the universe that physicists once held with great confidence, and they have forced a revision of theoretical frameworks that had stood for 100 years. The picture of physics that astronomers and theorists carried into the late 20th century is not the picture they hold now, and much of that change can be traced, directly or indirectly, to what we have learned from Sagittarius A star and the broader population of supermassive black holes it represents. The first casualty was the old idea that general relativity might fail in extreme gravitational environments. For most of the 20th century, there was a quiet, persistent suspicion among some physicists that Einstein's theory, beautiful as it was, would eventually break down when pushed hard enough. Near a black hole, the curvature of spacetime becomes so severe, the gravitational gradient so steep, that surely some new physics would emerge. Surely the equations would fail. Surely the predictions of general relativity, derived from a theory developed when physics did not yet know about quantum mechanics or nuclear forces, would diverge from reality in the strong field limit. They have not. Every test we have been able to perform, the orbits of stars near Sagittarius A star, the gravitational redshift of S2 during perihelion, the precession of stellar orbits, the geometry of the shadow imaged by the Event Horizon Telescope, the motion of flares around the inner accretion flow, has agreed with general relativity to within the precision of the measurement. Einstein's theory, formulated in 1915, continues to predict the behavior of the most extreme gravitational environments in our galaxy with no detectable error. This is not what most physicists expected. It is, in some ways, a more profound result than any single discovery. The theory has held up under conditions no terrestrial laboratory could ever produce, and it has held up perfectly. This is not to say that general relativity is the final word. Almost no working physicist believes that it is. The information paradox, discussed in earlier sections, indicates that general relativity and quantum mechanics cannot both be exactly right in their current forms. They predict different things about black hole evaporation, and the contradiction has to be resolved somehow. But the resolution, when it comes, will almost certainly involve refinements to general relativity that become important only at scales we cannot yet probe deep inside the event horizon or near the singularity itself. The everyday astrophysical behavior of black holes, including Sagittarius A star, appears to be described by Einstein's equations with no modification needed. The second casualty was the picture of galaxies as relatively passive collections of stars and gas, slowly evolving under the influence of self-gravity and a sprinkling of stellar feedback. That picture, still found in older textbooks, is gone. In its place is a far more dynamic, far more violent view of galactic evolution in which supermassive black holes play a central role. The M-sigma relation, the discovery of the Fermi bubbles, the prevalence of supermassive black holes in essentially every large galaxy, and the realization that those black holes can drive outflows powerful enough to reshape their host galaxies have collectively rewritten the story of how galaxies grow. In the new picture, a galaxy and its central black hole are not separate entities that happen to coexist. They are coupled. They grow together. They shape each other. When the black hole feeds, it heats and expels gas, suppressing star formation across the galaxy. When the galaxy provides fresh fuel through gas inflows or mergers, the black hole grows. The two are locked in a feedback loop that operates over timescales of hundreds of millions of years. The current quiet state of Sagittarius A star, that slow trickle of gas, those occasional flares, is not the natural condition of a supermassive black hole. It is a phase. A particular moment in a much longer history that has included episodes of dramatic activity and will, almost certainly, include such episodes again. The third overturned assumption was the idea that the conditions inside a black hole, however strange, were essentially a settled matter. The old picture, drawn from straightforward applications of general relativity, was that inside the event horizon, matter falls inexorably toward a central singularity, a point of infinite density and infinite curvature where the equations of physics simply give up. The singularity was an embarrassment, a clear sign that general relativity could not be the whole story, but it was assumed to be a localized embarrassment. Once a quantum theory of gravity came along, the singularity would be replaced by something sensible, perhaps a region of extremely high but finite density, perhaps a quantum scale knot of spacetime, perhaps even a connection to another universe. But whatever it was, it would be confined to the deep interior of the black hole, far from the event horizon, far from anything observable. That assumption has been shaken in recent years. Beginning around 2012, with the work of Ahmed Olmeri, Donald Maroff, Joseph Polchinski, and James Sully, a strong argument emerged that the standard picture of a smooth, featureless event horizon is inconsistent with the rules of quantum mechanics. To preserve information, to make Hawking radiation behave the way quantum mechanics demands, something dramatic might be required at the horizon itself, not in the deep interior, at the horizon. The argument, known as the firewall paradox, suggested that an infalling observer would not, as the textbook picture has it, cross the event horizon without noticing anything unusual. Instead, that observer would slam into a wall of intense quantum radiation, vaporized at the moment of crossing. The firewall proposal has been controversial. Most physicists do not quite believe it, but no one has been able to fully dismiss it either. What it represents, in a broader sense, is the breakdown of confidence about what black holes actually are. The smooth, well-understood object of classical general relativity is no longer the obvious answer. Strange alternatives have proliferated. Fuzzballs, in which the entire interior of the black hole is replaced by a tangled mess of string-theoretic structures with no sharp event horizon at all. Gravastars, exotic objects in which the interior is filled with a kind of dark energy that prevents true collapse. Black hole mimickers, objects that look exactly like black holes from outside, but lack a true event horizon altogether. For Sagittarius A star, this matters in a concrete way. If the standard general relativistic black hole is the correct description, then the central object in our galaxy contains a singularity, hidden behind the event horizon, where the laws of physics break down. If the firewall picture is correct, then there is no smooth interior at all, just a violent quantum surface from which information is somehow being radiated. If the fuzzball picture is correct, then what we call Sagittarius A star is actually a vast, tangled structure of fundamental strings masquerading as a black hole. The observations we have made so far cannot distinguish between these possibilities. The shadow looks the same in each scenario, at least to the precision the Event Horizon Telescope can achieve. The orbits of stars look the same. The flares look the same. The true nature of what lies inside is still hidden. A fourth overturned assumption concerns the role of black holes in the universe at large. For most of the 20th century, black holes were considered exotic, marginal objects, rare anomalies on the edge of cosmology, interesting to theorists, but largely irrelevant to the broader story of how the universe evolves. That view is also gone. Supermassive black holes are now understood to be central characters in cosmic history. They likely formed early. They influence the growth of galaxies. They produce gravitational wave backgrounds detectable across billions of light years. They may, according to some recent and still controversial proposals, play a role in the accelerating expansion of the universe through subtle effects on the surrounding spacetime. The cumulative effect of these revisions is that the universe of the 21st century looks dramatically different from the universe of the 20th. Black holes are not curiosities. They are pillars of cosmic structure. They are engines of galactic evolution. They are testbeds for fundamental physics. And the one at the center of our galaxy, the one closest to us, the one we can study in unprecedented detail, is a representative example of the most consequential class of objects in the known universe. Sagittarius A star has not just confirmed our theories. It has, in many ways, demanded that we build better ones. There is a question that, sooner or later, attaches itself to every discovery about Sagittarius A star. What does any of this have to do with us? Why should it matter to a human being living an ordinary human life on a small blue planet that a 4 million solar mass black hole sits at the center of our galaxy? The distances are unimaginable. The timescales are absurd. The black hole will not reach us. It will not consume us. It will not, in any practical sense, ever touch our lives. And yet, there are ways in which the presence of Sagittarius A star has shaped, and continues to shape, the conditions under which we exist. Ways that are not always obvious, and that took a long time for astronomers to recognize. The connection between the black hole at the center of our galaxy and the human beings looking up at it is not the distant, abstract connection that the geometry of cosmic distances would suggest. It is real, it is concrete, and it has consequences. The most immediate consequence is gravitational. Every object in the Milky Way is bound, ultimately, to the central black hole. The Sun, with all its planets, orbits Sagittarius A star at a distance of roughly 26,000 light-years, completing one circuit of the galaxy every 230 million years or so. Each of those orbits is called a galactic year. Since the Sun formed, about 4.5 billion years ago, the solar system has made roughly 20 trips around the galactic center. Since multicellular life first appeared on Earth, perhaps 3. Since the first hominids walked upright, perhaps a few thousandths of a single orbit. The dance is slow. The wheel turns at its own deliberate pace. But it turns, and Sagittarius A star is the axis it turns around. This is not merely a matter of gravitational poetry. The Sun's orbit around the galactic center carries it through different regions of the Milky Way at different times, and those passages have physical consequences. Periodically, the solar system passes through dense spiral arms, where the rate of nearby supernovae is elevated and the local cosmic ray environment changes. Periodically, it crosses the galactic plane, where dust and gas concentrations are higher, and the gravitational tides from nearby molecular clouds may have, in the past, disturbed comets in the outer reaches of the solar system, sending some of them into the inner planets. Several proposed extinction events in Earth's geological history have been tentatively linked to such passages, though the evidence remains contested. The orbit of the Sun around Sagittarius A star is in a real sense part of the geological history of our planet. A second connection is chemical. The atoms that make up your body were forged inside stars, the standard astrophysical cliché reminds us. But that picture is incomplete. The atoms in your body were forged inside stars, yes, but those stars existed within a chemical ecosystem that has been continuously enriched over billions of years by the activity of the galactic center. Every time Sagittarius A star has feasted, every time it has driven outflows and winds into the surrounding galaxy, every time the Fermi bubbles have inflated and faded, material has been cycled through the galactic medium. Heavy elements produced in massive stars near the galactic center have been mixed outward. Gas has been heated, then cooled, then condensed into new generations of stars. The Sun, formed from a cloud of gas about 4.5 billion years ago, inherited a chemical composition shaped, in part, by what Sagittarius A star had been doing for the previous 8 or 9 billion years of cosmic history. This is not a vague claim. The solar system contains specific isotopes, particular varieties of certain elements, that bear the signatures of supernovae, of stellar winds, of nuclear processes that occurred in environments dramatically different from anything in our local cosmic neighborhood. Some of those signatures appear to require enrichment from regions closer to the galactic center, regions where star formation was more intense and where the cycling of material through massive stars was more rapid. The iron in your blood, the calcium in your bones, the carbon in your DNA, much of it has a galactic history that loops, in some way, through the influence of Sagittarius A star and the violent processes it has driven over billions of years. A third connection is more philosophical, but no less real. The presence of a supermassive black hole at the center of our galaxy has shaped the conditions for habitable planets in ways that astrobiologists have only recently begun to appreciate. The central regions of the Milky Way are not friendly places. The radiation environment is harsh. Stellar densities are high enough that close encounters between stars are common, disrupting planetary orbits and stripping atmospheres. The intermittent feeding of Sagittarius A star produces bursts of energy that can sterilize nearby worlds, possibly out to distances of thousands of light years during the most violent episodes. Our solar system, fortunately, is far enough from the galactic center that we are insulated from these effects most of the time. We live in what astronomers sometimes call the galactic habitable zone, a region of the Milky Way far enough from the center to avoid the worst radiation, but close enough that the chemical environment is rich enough to support rocky planets and complex chemistry. The boundaries of that zone are set in part by the activity of Sagittarius A star. If the black hole had been more massive, more active, more violent over cosmic history, the habitable zone would have been pushed outward, and worlds at our distance from the center might not have been able to support life. If it had been less active, the chemical enrichment of the galaxy would have proceeded differently. and the materials needed for rocky planets and biological molecules might not have accumulated in the same way. In a strange and not entirely comfortable sense, then, we are here partly because of what Sagittarius A star has done, and partly because of what it has not done. Our existence is balanced on a fine line of galactic conditions, conditions that the black hole at the center of the Milky Way helped to establish over billions of years. There is one more connection worth naming, and it is perhaps the most important of all. The discoveries about Sagittarius A star, accumulated over the past 3 decades, have reshaped how we understand our place in the universe. Before the late 20th century, the center of our galaxy was a mystery, something to be wondered about, but not something that could be directly studied. The black hole's existence was inferred, its properties were estimated, its behavior was modeled, but it was, in some sense, theoretical, a creature of equations and indirect evidence. That is no longer true. We have photographed it. We have measured its mass to within a few percent. We have estimated its spin. We have tracked the orbits of stars around it for more than a generation. We have seen flares from gas falling into it. We have detected its shadow against the glow of its own accretion flow. The black hole at the center of our galaxy has been transformed, within a single human lifetime, from an abstract possibility into a concrete, measurable, observable object. It is not theoretical anymore. It is there. We can point at the photograph. We can name the stars whose orbits define its mass. We can describe, with reasonable confidence, what is happening within a few times the gravitational radius of its event horizon. This transformation is, in some ways, the most consequential thing about Sagittarius A star. Not what the black hole is, not what it does to galactic chemistry or planetary habitability, but what we have learned, by studying it, about what humans are capable of knowing. The center of the Milky Way, hidden behind a wall of dust, sitting at a distance and in conditions that no spacecraft will ever reach, has been opened up to direct examination. The instruments that did this, adaptive optics, interferometry, the planet-spanning Event Horizon Telescope, represent some of the most sophisticated engineering ever accomplished. The science that supports them, from general relativity to quantum field theory to the statistical analysis of imperfect data, represents some of the deepest theoretical work in the history of physics. We are, in other words, looking at Sagittarius A star not just with telescopes. We are looking at it with everything we have ever learned. The image of that orange ring around that dark shadow is, in some sense, a portrait of our species, of what we can do when we point our entire scientific civilization at a single point in the sky and refuse to look away. That, more than anything else, is what Sagittarius A star means for us. It means that the universe, however strange, is comprehensible, slowly, imperfectly, but genuinely. For all that we have learned about Sagittarius A star, there is a much longer list of things we do not yet know. The discoveries of the past 3 decades have not closed the file on the black hole at the center of our galaxy. They have, in many ways, opened it further. Each new measurement has revealed new puzzles. Each new image has raised new questions. And the missions and instruments now under construction, scheduled to come online over the next decade and beyond, are designed to push into territory that today's data cannot yet illuminate. The first and most obvious unanswered question concerns the interior. We have a photograph of the shadow. We have orbital data on stars passing nearby. We have the flickering signature of gas spiraling in toward its doom. But we have, by definition, no observations of anything that has actually crossed the event horizon. Whatever lies inside Sagittarius A star, whether a classical singularity, a fuzzball, a region of quantum gravitational structure we have yet to describe, remains beyond the reach of any conceivable telescope. No light escapes from inside. No information, by the strictest interpretation of general relativity, ever returns. Whether the resolution of the information paradox will eventually provide some indirect handle on the interior is an open question. For now, the inside of our galactic black hole is a closed book, and we do not even know whether the language it is written in resembles anything we currently understand. A second unanswered question concerns the spin in more detail. The initial measurements suggest that Sagittarius A star is rotating at a substantial fraction of the theoretical maximum, but the precision of those measurements is limited. The exact value of the spin, the precise orientation of the rotation axis, and the way the spin couples to the surrounding accretion flow are all subjects of ongoing investigation. Each refinement of these numbers tells us something more about the history of the black hole, about how many mergers it has experienced, about how much of its mass came from steady accretion versus dramatic events, about whether it has been twisted out of alignment with the galactic plane by ancient collisions we have no direct record of. The spin is, in some sense, the black hole's autobiography. Reading it more carefully will require improvements to the Event Horizon Telescope, including the addition of new participating observatories, new wavelengths of observation, and new techniques for processing the variable, fast-moving signal that distinguishes Sagittarius A star from the more stately black hole in M87. A third unanswered question concerns what astronomers call quasi-periodic oscillations, or QPOs. These are subtle, repeating variations in the brightness of black holes that appear in some observations and not others, with timescales related to the dynamics of the innermost orbits around the event horizon. If they could be detected reliably from Sagittarius A star, they would provide an independent measurement of the spin and a direct probe of the innermost, stable circular orbit, the closest distance at which gas can orbit before plunging inward. So far, claims of QPOs from Sagittarius A star have been tentative and inconsistent. Whether the black hole produces them consistently, whether the existing instruments are simply not sensitive enough to catch them reliably, or whether the highly variable accretion flow around our galactic black hole washes them out, remains unknown. Future observations with more sensitive X-ray telescopes, including missions like the European Space Agency's planned New Athena, scheduled for launch in the late 2030s, may finally settle the question. A fourth and particularly tantalizing question concerns whether Sagittarius A star might still surprise us in its day-to-day behavior. The flares are well documented now, but their detailed physics is not. We do not fully understand how the magnetic field around the black hole is structured, why the flares vary in amplitude the way they do, or what determines the relative brightness of flares at different wavelengths. There are also occasional reports of stranger events, sudden brightenings that exceed the typical flare brightness by additional factors, unexplained correlations between activity in different parts of the electromagnetic spectrum, hints of structural changes in the radio source that may indicate larger episodic instabilities. Whether any of these are real and what they imply will require continued long-term monitoring across many telescopes, year after year. A fifth question concerns the broader environment around Sagittarius A star. The black hole does not sit in isolation. It is surrounded by a remarkable population of stars, gas clouds, and exotic objects whose behavior continues to puzzle astronomers. Among the most mysterious are the so-called G-objects, strange, dusty entities first identified in 2012, which appear to be passing close to Sagittarius A star and surviving in ways that should not be possible. They look like compact gas clouds, but they behave like stars. They have stretched out as they passed near the black hole, but they have not been torn apart. Their nature remains contested. Some astronomers think they are puffy young stars enshrouded in dust. Others think they are merger products from earlier stellar collisions in the dense central region. Still others suspect they are something else entirely, a class of object that exists only in the extreme environment near a supermassive black hole, with no analogue elsewhere in the galaxy. New G-objects are still being discovered, and each one adds another data point to a puzzle that has not yet been solved. A sixth question concerns the past activity of the black hole. The Fermi bubbles, those enormous structures of gamma-ray emission extending above and below the galactic plane, are clearly the residue of an ancient episode of dramatic activity at the galactic center. But how long ago did that episode happen? How long did it last? Was it powered by a single dramatic feeding event, perhaps the disruption of a large gas cloud, or even the consumption of an entire star, or by a more extended period of enhanced accretion? The answers will require better modeling of the bubbles themselves. better understanding of the magnetic fields and cosmic rays that permeate them, and possibly the discovery of new structures deeper in the galactic plane that record earlier episodes still. Some preliminary evidence suggests that Sagittarius A star may have been substantially more active as recently as a few hundred years ago, bright enough that, had humans known where to look, the central engine of our galaxy might have been visible in ways it is not today. A seventh question, perhaps the most ambitious of all, concerns whether Sagittarius A star can be used as a laboratory to test theories of quantum gravity. The shadow imaged by the Event Horizon Telescope is, to our current precision, perfectly consistent with the predictions of classical general relativity. But there could be tiny deviations, corrections introduced by quantum effects at the event horizon, or by alternative theories of gravity that modify Einstein's equations in subtle ways. Detecting such deviations would be one of the most important results in the history of physics. It would tell us, for the first time, that general relativity is not the final word, and it would provide a concrete experimental anchor for the development of a true quantum theory of gravity. Achieving the necessary precision will require continued upgrades to the Event Horizon Telescope, including the addition of space-based interferometric elements that would extend the effective baseline beyond the diameter of the Earth itself. Proposals for such missions, under names like the Black Hole Explorer, are in active development. If they fly, they may produce images of Sagittarius A star with 10 times the resolution of the current ones, opening windows into the strong field regime of gravity that no terrestrial experiment can match. Finally, there is the question of what we will learn by simply waiting and watching. The S stars continue to orbit. S2 will swing back through its perihelion in a few more years, and each new passage allows for refinements of the measurements that constrain the mass, the spin, and the gravitational potential of Sagittarius A star. Other stars, with longer orbital periods, will reach their own closest approaches over the coming decades, providing entirely new geometries against which to test relativity. The Event Horizon Telescope is moving toward producing not just still images, but movies, sequences of frames that capture the changing structure of the inner accretion flow on hourly and daily timescales. Over the next 10 years, we will have, for the first time, a moving picture of a black hole, not a single frame, a film. The list of unanswered questions, in other words, is long, and that is not a sign of failure. It is a sign that the field is alive. There is a moment, if you spend long enough thinking about Sagittarius A star, when the technical details fall away and you are left with something simpler, something older, something closer to the way human beings looked at the sky for most of our history, before we had telescopes or equations or any of the apparatus that has, in the past century, transformed the night sky from a source of mystery into a subject of measurement. That moment is the realization that, right now, as you sit reading this, there is a hole in the universe at the center of our galaxy. A real hole. A region where the rules we live by no longer apply, where the substance of space and time is so distorted that the very ideas of inside and outside, before and after, here and there, lose their ordinary meaning. And around that hole, the entire Milky Way is turning, like water circling a drain that never empties. It is difficult, when you let yourself think about this seriously, not to feel something. The feeling is not quite fear, because the black hole is not a threat. It is too far away and too slow and too quiet to harm us. The feeling is not quite awe exactly, though awe is part of it. The feeling is closer to what some philosophers have called the sublime, the particular response humans have to encountering something vastly larger and stranger than ourselves, something that exceeds our ability to fully comprehend it, and yet that we are forced to acknowledge as real. For most of human history, we did not know any of this was there. The ancient skywatchers of every culture, the Egyptians who built their temples aligned to the rising of Sirius, the Polynesian navigators who crossed thousands of miles of ocean by reading the stars, the medieval astronomers in Baghdad and Beijing who catalogued the heavens with painstaking precision, looked up and saw what looked like a fixed firmament. They saw lights. They saw patterns. They did not see, because they could not see, the thing the patterns were arranged around. The center of the Milky Way was visible to them, on dark nights, as a hazy band of pale light running through the constellation Sagittarius. They had no way to know that the haze was the combined glow of billions of stars, and they had no way to know that all those stars, and the haze itself, and the long arms of our spiral galaxy, and our own sun and Earth among them, were all being held in place by an invisible giant. We know now. We are, in fact, the first generation of human beings to know, the first to have photographs of it, the first to have measurements of its mass and spin, the first to be able to point, with mathematical precision, at the place in the sky where our galaxy hinges. Every person who has ever lived before us, every philosopher, every poet, every farmer who ever looked up at the stars and felt something stir in them, did so without knowing what was really at the center of it all. And we, alive in this brief moment of cosmic history, do know. The knowledge is barely older than some of the people reading this. It would have been considered a wild fantasy at the time some of our grandparents were born. This is, in some ways, the deepest reflection that the story of Sagittarius A star invites. Not what the black hole is, but what it means that we are here at this particular moment with this particular knowledge. We are not the most important beings in the universe. We are not even, by any cosmically reasonable measure, particularly important at all. We occupy a small planet around an ordinary star in an unremarkable arm of an average spiral galaxy, 26,000 light-years from the center, a long way from the action. And yet, by some accident of curiosity and patience and craft, we have managed to look across that distance and see what is there. We have managed, in the words of an astronomer once asked to describe the achievement, to take the universe's measurements. There is a kind of dignity in that. Not the dignity of mattering cosmically. The universe does not seem to be arranged for our benefit, and there is no evidence that anything beyond Earth particularly cares whether we exist. But the dignity of having tried, of having looked, of having refused, when faced with the wall of dust at the center of our galaxy, to simply accept that the answer was hidden forever. We built telescopes. We invented adaptive optics. We linked observatories across continents into a single planet-sized eye. We spent 30 years tracking the orbits of stars we could not even see with the naked eye, just to confirm what they were orbiting. And at the end of that work, we held in our hands an image, a real photographic image of the black hole at the heart of our galaxy. That accomplishment does not change anything about the universe. Sagittarius A star was there before we knew. It will be there long after we are gone. Its mass, its spin, its slow consumption of nearby gas, its gradual evaporation into Hawking radiation across timescales that dwarf the current age of the cosmos by uncountable factors, none of this depends on us. We are not necessary to the story. We are at best a small, brief audience, but we are an audience, and the act of paying attention, of caring enough to look, and look carefully, and keep looking even when the answers come slowly, is not nothing. It may be one of the things that most distinguishes our species. Not the only thing, but one of them. Other animals have language, and tools, and social complexity. Other animals have culture in some forms, but it is not clear that any other species spends generations of effort trying to understand what is happening at the center of the galaxy. That particular kind of curiosity, the kind that looks past every immediate concern toward something distant and beautiful and useless, seems to be ours. There is also something humbling, even unsettling, about the position the discoveries place us in. We can describe Sagittarius A star in detail. We can model its gravitational field, predict the orbits of stars passing near it, calculate the rate at which gas falls into its accretion disk, estimate the spin of its rotational axis. And yet, we do not know what is inside it. We do not know what happens to the information that crosses its event horizon. We do not know whether, in some deep sense, the black hole is even what general relativity says it is, or whether it is something stranger that we have not yet learned to imagine. This combination, knowing so much, while remaining ignorant of so much, is, in some ways, the characteristic condition of modern science. We have built an extraordinarily detailed picture of the universe. We have learned things our ancestors would have considered miraculous. And we have also, by learning them, sharpened our understanding of just how much remains beyond our reach. The horizon of human knowledge has expanded enormously, but so has the horizon of human ignorance, because every new discovery reveals new questions that were not visible before. Sagittarius A star, in this sense, is the perfect symbol of our situation. It is the most thoroughly studied black hole in the universe, and it is also, in its deepest essence, completely opaque. We have its photograph, and we still do not know what is inside it. We have its mass to within a few percent, and we cannot say what its singularity, if it has one, is actually made of. We have measured the bending of light around its edge, and we have not solved the paradox of how it can both consume information and preserve it. The center of our galaxy is the best metaphor we have for the limits of what we can know. It is also a demonstration that those limits can be pushed, century after century, by patient effort and careful instruments and the slow accumulation of insight. Both things are true at the same time. And both things together are what it means to live in a universe that contains Sagittarius A star. The story of Sagittarius A star does not end. That is the strange thing about it. Most stories end, even cosmic ones. Stars are born, they shine, they exhaust their fuel, they die. Galaxies form, they evolve, they merge, they fade. The universe itself, according to our best theories, is heading toward a long, cold dispersal, a final state of maximum entropy in which nothing interesting happens anymore. Within that vast arc, there are beginnings and endings, narratives that resolve, chapters that close. But not for Sagittarius A star, not for the black hole at the heart of our galaxy. Long after the sun has expanded into a red giant and consumed the inner planets, long after the Earth has been swallowed or scorched into a lifeless cinder, long after the Milky Way has collided and merged with Andromeda and become some other, larger galaxy entirely, Sagittarius A star will still be there. Larger by then, heavier, combined, almost certainly, with whatever supermassive black hole the merger brings into contact with it, still spinning. Still feeding in the slow, patient way that supermassive black holes feed across cosmic time. Still pulling the bones of the merged galaxy into a quiet, gravitational waltz around itself. It will outlast almost everything. When the last stars in the universe burn out, trillions of years from now, and the cosmos enters what astronomers sometimes call the degenerate era, a long, dim epoch dominated by white dwarfs, neutron stars, and stellar remnants, the supermassive black holes will still be there. When the white dwarfs themselves slowly cool into dark, inert objects, and the universe enters the so-called black hole era, Sagittarius A star and its cousins will be the dominant features of cosmic structure, drifting through an increasingly empty space, occasionally consuming each other through gravitational mergers that release ripples in spacetime detectable across the entire observable universe. And only then, in timescales that dwarf the current age of the universe by factors so vast that no human notation can adequately express them, will the slow drizzle of Hawking radiation finally erode the black holes themselves into nothing. This is the deep time perspective that Sagittarius A star demands. The black hole is older than almost everything we care about. It will be younger than almost everything that comes after us. Our entire species, from the first hominid to whoever might be the last, will occupy a window of cosmic history shorter than a single sentence in the autobiography of our galactic black hole. We are a flicker. The black hole is the candle. And yet, and this is the strangeness that the story keeps circling back to, we have seen it. We have measured it. We have, in our brief flicker of existence, managed to take its measure. The fact that this is even possible says something, finally, about the universe and about ourselves that no other discovery quite captures. The universe is the kind of place where, given enough time and enough effort, even creatures as small as we are can come to know something about even objects as vast as Sagittarius A star. The structure of physical reality, whatever else it may be, is comprehensible to minds that arose from chemistry on the surface of a wet, blue planet around an ordinary yellow star. That is, on reflection, an astonishing fact. It did not have to be that way. The universe could have been incomprehensible. It is not. What lies inside Sagittarius A star, then? We do not know in the deepest sense. The mathematics suggests a singularity. a point or a ring where density and curvature become infinite, where the equations of general relativity break down, where some unknown quantum theory of gravity must take over. The information paradox suggests that something subtler is happening, that information falling in must somehow be preserved, that the smooth event horizon of classical theory may need to be replaced by something with structure, something that remembers what it has consumed. The newer ideas, fuzzballs, gravastars, holographic projections, suggest that the very concepts of interior and exterior may not apply in the way our intuitions demand. The honest answer is that we do not yet know which of these is closest to the truth, or whether the truth is something none of them has anticipated. But we know enough to say this. Whatever is inside Sagittarius A star is not nothing. It is the densest concentration of matter and energy our galaxy contains. It is the gravitational anchor of every star around us. It is, by the strange logic of black hole thermodynamics, one of the highest entropy objects in the universe, a place where information piles up, somehow, in ways the equations are still working to describe. It is the closest thing in our neighborhood to a true cosmic horizon, a boundary between what can be known and what cannot. And it is real. It is not a theoretical construct. It is a physical object that we have photographed, measured, and named. If you go outside tonight, and the weather is clear, and you happen to live somewhere with dark skies, you can find it. The constellation Sagittarius rises in the southern sky in summer in the northern hemisphere, higher in the south in winter from places below the equator. Within it, you can locate the dense band of the Milky Way, where the galactic center hides behind its veil of dust. Even on the best night, you cannot see Sagittarius A star directly. The light from that direction is dimmed by a factor of more than 1 trillion before it reaches our atmosphere. But it is there. The black hole is there, behind the dust, behind the stars, at the still point of the wheeling galaxy. You can point at the place where it is, even if you cannot see it. And knowing that it is there, knowing what it is, knowing what we have learned about it across the past 100 years of effort, changes, in some small way, what it feels like to look up at the sky. That, in the end, may be the most lasting gift that Sagittarius A star has given us. Not its scientific implications, important as those are, not its role in shaping the conditions for our existence, but the simple, profound shift in perspective that comes from knowing that the universe contains such an object and that we have managed, against considerable odds, to find out something about it. We are smaller in the light of that knowledge. We are also somehow larger. The two feelings come together. They do not cancel out. They simply coexist, the way the calm of a still afternoon coexists with the awareness that, just out of sight, the world is full of immense and ancient things doing immense and ancient work. Sagittarius A star is one of those things, the most local of them by an enormous margin, the closest supermassive black hole to Earth, and the only one we will ever be able to study in this kind of detail. There may be other intelligent species elsewhere in the universe who have made similar discoveries about their own galactic centers, and there may not. We have no way to know, but we know about ours. We have seen ours. We are, for now, the only species in our part of the cosmos that can be said with certainty to know what is at the heart of its own galaxy. That is something. It is not everything, but it is something. Thank you for taking this long journey with me. The road has been winding, and the destination has been, in some ways, an admission of how much more remains hidden than has been revealed. But if anything in this story has stirred something in you, a sense of wonder, a flicker of curiosity, a desire to look up at the sky and find Sagittarius again, the way human beings have done for thousands of years, then the journey has been worth the time. If you found something of value here, consider leaving a like, sharing this video with someone who would also appreciate it, and subscribing to come along for the next exploration. The universe is enormous and full of strange and beautiful objects, and we have only just begun to know them. There will always be more to find. There will always be more to wonder about. There will always be at the center of our galaxy that quiet, ancient giant turning the wheel, holding the silence, keeping its secrets. Until next time, keep looking up.